Hello everyone, my name is Vedanth, BSMS Physics third year. Today I'm going to tell you about my ML project on autonomous quadrotor simulation using Unity and Python with ML agents. So, first of all, what is a quadrotor? It is a four-rotor aircraft capable of vertical takeoff, hovering and autonomous flight through coordinated motor control. Why to simulate it first? Before going to the hardware part, simulation is the safe and cost-effective training environment for developing autonomous flight algorithms, as we can alter the algorithms or change the algorithm. In my project, I am using Unity plus Python, which combines real-time physics simulation with machine learning for intelligent drone behavior development. The technologies used are Unity for real-time environment physics engine and 3D visualization for drone simulation. Second, Python for reinforcement learning algorithms and ML agents interface for training autonomous behavior. Then, for drone motion scripting and control logic implementation within the Unity environment, we are using C Sharp. Quadrotor flight principles. So what are the principles of quadrotor on which it runs? First, the flight mechanisms. Lift, thrust, torque work together to achieve stable flight and directional control. Then comes the physics application. Applying aerodynamic principles enables stability, precision maneuvers, and autonomous navigation. In this, we got hands-on learning in Unity simulation to provide interactive environment to test the flight dynamics and control algorithm. Then comes the physics simulation and control implementation. So let's dive into the physics of the drone or the quadrotor. First, physics parameters. Precisely modeled as mass, drag coefficient, individual motor thrust characteristics for realistic flight behavior. And then comes control input mapping, which translates high-level commands like desired position, velocity into PWM signals for each motor mimicking real-world joystick or keyboard inputs. Then, for stability of algorithms, we use advanced PID controls and Kalman filters for real-time state estimation or agile stabilization against external disturbances. Through PID, we can send many different values of PID from which we can get stability through PD, PX, and PW. Real-time performance. Optimized simulation loop ensures low latency feedback, critical for accurate AI training and dynamic response within the virtual environment. Our system meticulously handles physics calculation for thrust, roll, pitch, and yaw control, ensuring realistic drone behavior. The agent receives positional input to control movement, translate high-level commands into precise motor action. This setup involves real-time force calculation and movement dynamics, crucial for accurately simulating the quadrotor's interaction within the environment. ML agents simulating quadrotor behavior. First, ML integration embedded machine learning directly into drone simulation for adaptive learning. Then the real-world application. We can engage with practical AI use cases in autonomous system and robotics. Then autonomous training. Drones learn to stabilize, hover, and navigate through reinforcement learning. Then comes the Unity Python integration workflow. First, Unity scenes simulation the environment, then Python trainer the algorithm. Training logs the performance data, ONNX model which is for train weights, and then inference the live control. In this video, we can see we have set up a Python environment for ML agents to activate within the Unity software, so we can be connected with the Unity software in the Python environment. As you can see, we need to use Conda activate ML agents to activate within Python 3.9. To mention the point, Python 3.10 and above are not supported in this ML agents for these ML agents. And in pip installer 1.23 and above are not supported for this ML agent, so preferably 1.21 XX are mostly preferred for this environment. The simulation in Python. Build the Unity simulation. First, prepare your Unity environment by navigating to File, Build setting, and exporting the project as an executable. This is a standalone application will host you simulated drone environment for Python to interact with it. Set up the Python environment as I have shown the video above. We can set up the Python environment by create an ML agents Python equal to 3.9, then activate it and install necessary ML agents package using pip install ML agents underscore ems dot. Then we can run with our Python code, integrate the Unity simulation with Python using Unity environment and Unity to Gem wrapper to create a Gem compatible environment. Below is the example how to initialize the environment. This setup the communication bridge allowing the Python to send commands and receive observations from Unity simulation. For seamless communication in AI, the established integration ensure seamless real-time communication between Unity and Python. The bidirectional data flow is critical for effective AI training, allowing the Python-based reinforcement learning algo to interact dynamically within the Unity simulation, iteratively refine agent behaviors, and enable robust autonomous control. As we can see this, the first picture is Unity Hub in which we have set up our project Quadrotor and we have launched it to the Unity native app in which we have set up the environment. We have test, train and implement the model in which we have worked on. Then we can find uh, when we go to build settings in within the Unity and set up for the OS which you are in. Currently, I was using Mac OS Tahoe, so I have set up for Mac and Mac Silicon, and then I build it and run it, build and run. So then I got a Core Router simulation app in which I simulated and I got the autonomous Quadrotor training, which shows the real-time learning as the drone masters precise hovering and complex flight maneuvers within a dynamic virtual environment. Witness the AI's iterative progress and stability achieved through ML agents. As you can see, the drone itself taking the path and avoiding the obstacles. Now we got to learn about reinforcement learning training process. For drone control, reinforcement learning is exceptionally effective due to its ability to optimize complex continuous control policies through trial and error. First, we go on reward function breakdown. The reward function is critical guiding the AI by providing positive reinforcement for desired behaviors like hovering or reaching targets and negative penalties for undesirable actions. This iterative feedback loop is how the AI learns to achieve precise control. Training loop environment agent. Our system facilitates a continuous training loop where the agent called Quadrotor AI interacts with Unity-based simulation environment. It observes the state, takes action, and receives rewards, constantly refining its control policy through deep reinforcement learning algorithms, collision handling, and boundaries. To ensure robust and safe autonomous flight, the simulation includes explicit collision handling and boundary definitions. The AI is penalized for collision with virtual obstacles and exceeding defined flight boundaries, teaching it to operate safely within the operational space. As you can see, we have used this particular RL model. Our autonomous quadrotor is built within Unity, providing a rich visual interface for observing drones' behavior. The environment displays real-time data and visual cues that are crucial for monitoring training processes and understand how the AI agent interacts with its surroundings. This interface allows us to visualize progress and identify the areas of improvement and fine-tune our parameters efficiently. The results, as you see, the results stable hover achieved the drone was successfully maintained its altitude and position after training convergence. Reward tuning impact fine-tuned reward functions significantly improved control precision and responses. Data flow confirms seamless communication between Unity and Python validated as we have integrated in its architecture. For future enhancements, sensor integration. The most important part is sensor integration, for which the most important option is LiDAR or camera sensor. In LiDAR sensor, we can also use LiDAR SLAM, which is simultaneous localization and mapping. And we can also do multi-drone coordination, develop swarm algorithms for collaborative flight and coordinated mission planning. Hardware testing, deploy the trained models to drones via ROS and PX for integration for validation. Now we get to see about the simulation in Ubuntu. We use here Ubuntu and AirSim and RL setup, particularly in here. First, we need to get Ubuntu environment setup, which meets the necessary requirements for AirSim and Unreal Engine. Install the dependencies as given below. This ensures you core tools for compiling AirSim from source and managing other packages. Next comes AirSim installation. Installing AirSim by cloning its GitHub repo and building it from source. This process also typically involves setting up Unreal Engine for simulation environment. Next, RL integration. Establishing your Python environment for interacting with AirSim and implementing reinforcement learning algorithms creates a dedicated Conda environment. As we have done in Unity, we need to set up the same Python environment in here also for the ASM packages to provide API to control rules, while Zim and stable based library packages are standard for R development. Then training and implementation. With AirSim installed and the Python environment ready, you can now implement RL training loop. This involves connecting to AirSim simulation, defining observation and action spaces, and running the training processes, as we have seen through the code below. In this particular simulation, we have used Unreal Engine plus AirSim for 3D realistic drone world simulation. PX4 and SITL, which are software in the loop, drone autopilot, and firm running inside the software. We can either use Mavlink or MavSDK for communication protocol between drone and ground control. We can use Q ground control or MapProxy for displaying the telemetry like altitude, GPS, or speed. Python controls custom AI logic to control or train the drone. Gazebo and ROS are optional for used for robotic middleware or sensor data recognition. In this particular simulation, we have set a target for drone, so it autonomously hovers and reaches its destination, which was set through the AI model. This setup is completely AI-based drone simulation environment, designed to replicate the real-world quadrotor behavior in safe and virtual space. It combines several powerful tools work together to simulate physics, control, logic, and autonomous decision making. The foundation of the simulation is built using Unreal Engine and Airstream, which together create a high-fidelity 3D with realistic physics and sensor data. The PX4 and SITL software in the loop runs the drone's autopilot firmware virtually, enabling the realistic flight behavior without needing a physical hardware. Communication between the simulated drone can be done through MavLink or MavSDK, and Q-ground control can transmit the telemetry data as attitude GPS coordinates. For monitoring and manual control, Q-ground control and Mav proxy serve as ground control interface which display live flight data like mentioned above and the system status. Python control script integrate custom AI algorithms such as PID controllers and reinforcement learning models, which allow the drone to make autonomous decisions like path following, target tracking, or stable coding. Additionally, Gazebo or ROS can be optionally integrated to advanced capabilities like multi-drone coordination, sensor fusion, SLAM-based navigation. As we have discussed before, SLAM-based navigation can be done through LiDAR SLAM or visual SLAM through camera sensor or LiDAR sensor. Overall, this setup provides a powerful test bed for developing and validating AI-driven flight control system. It allows researchers and students to train and test and visualize the drone under realistic conditions, bridging the gap between simulation and real-world deployment. As per the conclusion, reinforcement learning enables adaptive flight control through intelligent simulation. Effective integration, Unity ML agents, Python creates the powerful learning loop for autonomous system. AI-driven simulation demonstrated autonomous quadrotor controlling using advanced AI techniques. Future-ready foundation established for advanced robotics research and real-world development. So that was my project on autonomous quadrotor simulation using Python and Unity for macOS and AirSim Unreal Engine PX4 SITL Q-ground control in Ubuntu OS for bridging simulation, machine learning, and autonomous flight control. First one, Unity with Unity and Python in macOS to follow the track and pass through the obstacles, pass avoiding the obstacles, sorry, and the Ubuntu one for reaching the target position. So thank you everyone.